Hello, everyone. My name is Vahid. Last year here at HHL conference, I presented the first stage of this project, but now that we have finished it, I am excited to share more complete results with you. A few years ago, we met with FEMA employees who worked in Puerto Rico during Hurricane Maria. And immediately after the hurricane, they ordered a ship filled with fuel to be sent from Louisiana to the port of San Juan in Puerto Rico. Based on that experience, they proposed a plan to use ships to help with quick fuel distribution on the island for future disasters. And the title of this presentation was what they were looking at that time, and we wanted to look at how they could do it most efficiently. So we started to conduct some interviews with them to help them better prepare for future disasters. And we provided a case study based on the real data that we obtained from them. These two document sheets are two examples of the data that we received from FEMA, and most of them belong to their long-term fuel distribution strategy to deliver fuel from mainlands to some specific locations on the island called dispensing sites, fuel dispensing sites, that are some locations with large tanks, and the locations are determined by FEMA based on the island's population centers, the locations of the population centers. Even though those locations are determined by FEMA, there remain some important questions that need to be answered. For example, how many ports should be visited? In this picture, I tried to show what happened after Hurricane Maria. As you see, the whole island was served through only one port, but after the disasters, due to the damage to the road infrastructure, it may not always be optimal to serve the whole island through only one port. We may be able to provide a better and faster service if the ship visits more than one port. But as soon as the ship visits more than one port, the next important question that arises is that now what's the optimal assignment of the dispensing sites to those ports? Because now, for example, dispensing sites 8 and 9 that are being served by port 1, now they can be, for example, served by port 5, and this may provide a better service and better solution for us. Another important question is that which ports should be visited by the ships. And even if visiting these 3 ports in this example, ports 1, 5, and 2, even if visiting them is optimal, and even if this assignment of the dispensing sites to those ports is optimal, the next important question is that now what's the optimal routing structure of the ship? Here, these 3 ports are being visited in a clockwise fashion, but for instance, the ship can visit them in a counterclockwise fashion, and it may provide a better solution. All these questions still hold if we have more than one ship, if we have 2, 3, 5, or even more number of ships. And last but not least, we want to know what is the impact of the departure point of the ships. As I mentioned, after Hurricane Maria, the ship delivered fuel from Louisiana, Port Fuchon, but based on our interviews and conversations with FEMA, the ships can also deliver fuel from Port of Jacksonville in Florida. So we added these 2 mainland ports to our model as the departure points or the origins of the ships. Also inspired by some real world examples of standby ships around islands ahead of hurricanes, we developed a special case of the problem. So these standby ships are equipped with relief items that they can stand by in the area ahead of the hurricane close to the island to carry out a quick response in the event of a disaster. But the use of these ships was not part of FEMA's plan. We thought it's a new idea worth exploring to see how it can impact the quality of services. So to answer these questions, we developed a mixed integer programming model that represents an intermodal transportation network, including sea and road transportation modes. And the objective is to minimize the maximum of arrival times over all dispensing sites. And by reducing it to the dominating set problem, we prove that it's an NP hard problem. But to better understand how the arrival times are calculated at those dispensing sites, I provided a very simple example. Assume this island has only 2 ports, Q and L, and this assignment, just suppose that this assignment is the optimal assignment in the optimal solution. And I just want to use this example to show how, for example, we can calculate the arrival time at dispensing site number 4. So the arrival time is based on the sea travel time to reach the associated port. For site 4, the associated port is port L, because it's being served by port L. So we will have a travel time, sea travel time from port P to port Q, and then from port Q to port L. But when the ship arrives at port Q, there is a filling time to load the trucks that are required to satisfy the demand of the first 3 dispensing sites that are being served before site 4 to port Q. And the ship cannot leave port Q until all of them are loaded. And when all of them are loaded, the ship goes to port L. There will be another filling time to load the trucks required for site 4 now. And when the last truck is loaded, it incurs a road travel time from port L to site 4. And when the last truck arrives at that particular site, that would be the arrival time at the site. So before going to our computational results, I would like to explain one of our most important analytical results. We could prove that it's always optimal to serve the dispensing sites that are assigned to the same port in order of furthest to the closest. By furthest, I mean furthest in terms of road travel time. In this example, suppose this site, all of these 3 sites are assigned to the same port, port P, and assume that this one is the furthest one from port P in terms of road travel time. This one is the closest one. So in this example, we prove that it's always optimal to serve them in this order. At first, we should serve the furthest one, then the middle one, and in the end, we serve the closest one to port P. And there might be alternative solutions, but we prove that this order is never suboptimal, and it helps us to reduce the size of the search space and significantly reduce the solution time by almost 58%. For our computational experiments, as I already mentioned, we have 2 mainland ports as our origins located in Louisiana and Florida, and also we have a set of instances by considering the use of standby ships. We consider different number of ships to see the impact of this parameter. There are also other parameters in our instances, but the optimal solutions, the structure of optimal solutions, we're not very sensitive to the small changes in parameters. So in this presentation, I will focus on these 2 first and most important parameters. So the results show that FEMA can reduce the service time by almost 21% if they deliver fuel from Florida, Port of Jacksonville, instead of Port Fuchon. Also, standby ships can help us to reduce the service time by almost 72%. That was one of the main findings in this research and had a huge impact on the service time. Here you can see the impact of the number of the ships, and each bar here shows the percentage difference ratio relative to the 1 ship case to quantify the change. And as you see, the improvements are significant for all origins and for all number of ships, but are largest with the standby ships. And that's it. So I just want to provide a thank you again, and I appreciate everybody watching this presentation. also to my advisor, Professor Campbell, who was extremely supportive. Thank you, and I appreciate your time.